Hello everyone, I'm so excited to start our journey into the world of system design today. In this session, we're going to pull back the curtain on how massive digital platforms are built to handle millions of users simultaneously. I like to think of system design as city planning. You wouldn't just start stacking bricks to build a skyscraper without a blueprint, right? Similarly, for digital systems, we need a high-level plan to ensure everything from the plumbing to the electricity of our data works together seamlessly. Look at this visual. Just as a city scales from individual houses to a bustling metropolis, our architecture must allow a system to grow from a few users to a global audience without collapsing under its own weight. To master this, we have to understand the core building blocks. These are the fundamental components that every senior engineer uses to solve complex problems. Throughout this course, we'll be exploring these 5 pillars: client-server architecture, load balancers for traffic management, databases for reliable storage, and caching and CDNs to keep things lightning fast for users everywhere. Remember, true scalability depends on how effectively these individual pieces interact. If we understand the blocks, we can build anything. Let's dive into our first concept. Building on that overview we just discussed, let's dive into our first building block, the client-server architecture. This is the bedrock of how nearly every modern application functions. If you look at this diagram, you'll see the 2 main players in this environment. On one side, we have the client. This is the requester. Think of the browser you're using right now or a mobile app on your phone. The client's job is to initiate the conversation by sending a request. The server, on the other hand, is the resource provider. It houses the API and the database, waiting to process that request and send back a response. This back and forth is known as the request-response cycle. Now, there is a specific rule to this interaction that we call statelessness. It's a key concept in distributed systems. Essentially, it means the server treats every single request as a brand new interaction. It doesn't remember what you did a moment ago by default. While that might sound a bit forgetful, it actually makes the system much easier to scale because any server can handle any request. We'll see exactly why that's so important as we move on to scaling and load balancers next. Building on what we just covered regarding basic client-server setups, let's look at what happens when your application starts to grow. One server might be fine for a few users, but as we scale up, our architecture needs to evolve. The biggest risk with a single server setup is that it's a single point of failure. If that one server crashes or needs a reboot for updates, your entire business goes dark. In professional system design, we want to eliminate these bottlenecks. To solve this, we introduce the load balancer. Think of it as a traffic cop standing at a busy intersection. It intercepts every incoming request and decides exactly which server in your fleet is best equipped to handle it at that moment. If you look at this architecture diagram, you'll see the load balancer sitting right in the middle. It ensures that no single server gets overwhelmed while others are sitting idle. It's all about spreading the workload evenly. By doing this, we achieve high availability and reliability. If one server goes down, the load balancer simply stops sending traffic there and redirects it to healthy servers. This is the secret to horizontal scaling, adding more power just by adding more machines. Before we move into our interactive lab to see this in practice, are there any questions on how the traffic cop decides where the data goes? Let's see them in action. In front of you, we have a simulation where incoming requests, those colored balls, are being routed to our 4 servers. Notice how the server bars fill up as they process the load. Start by selecting the round robin button on your control panel. Watch how the requests are distributed sequentially, one after the other, regardless of how busy a server already is. It's simple, but keep an eye on those CPU load bars. Is the work truly balanced if some requests take longer than others? Next, switch over to least connections. Notice the difference? The load balancer is now making a smarter choice, sending new requests to the servers that currently have the most available capacity. This is a great example of the dynamic routing we just covered on the previous page. To see how resilient this system is, try killing one of the servers by clicking on it. You'll see the traffic immediately reroute to the remaining healthy servers. This shows why load balancers are so critical for high availability. They ensure our users don't experience any downtime even when hardware fails. Take a moment to experiment with the different algorithms and see how they handle sudden bursts of traffic. Once you feel comfortable with how these distribution patterns work, we'll move on to see if you can identify the best strategy for different system scenarios. Now that we've explored how to balance traffic across our servers, we need to talk about where all that data actually lives. Choosing the right storage solution, SQL versus NoSQL, is one of the most critical decisions you'll make in system design. First, let's look at SQL, or Relational Databases. Think of these like a very strictly organized filing cabinet. They use structured data and adhere to ACID compliance, which ensures that transactions are processed reliably. If you are handling complex queries or financial data where consistency is king, tools like PostgreSQL or MySQL are your best friends. On the other hand, we have NoSQL, which is non-relational. These are built for flexibility and massive scale. Instead of a fixed structure, they use a dynamic schema, making them ideal for unstructured data or rapidly changing requirements. When you need to scale out across hundreds of servers, databases like MongoDB or Cassandra really shine. Take a look at this comparison table. The key takeaway here is the trade-off. SQL generally scales vertically by adding more power to one machine, while NoSQL scales horizontally by adding more machines. It's not about which is better, but which fits your specific use case. Whether we pick SQL or NoSQL, sometimes the disk is just too slow for our needs. So, building on this, let's move forward and see how we can use caching to give our system a real performance boost. Building on what we just covered regarding the speed limitations of traditional disks, let's explore how we can achieve a massive performance boost using caching, specifically with Redis. So, why do we need caching? The primary goal is to reduce latency. While databases are great for persistence, they are often on disk. Redis, however, keeps data in memory, allowing for millisecond response times. By serving these requests from memory, we also significantly reduce the load on our primary database, preventing it from becoming a bottleneck as our traffic grows. Let's look at 3 very common ways we use Redis in modern system design. First, session management. When a user logs in, we need to check their session on every single page request. Moving those sessions to Redis ensures the user experience remains snappy and the database isn't constantly pinged just for authentication. Next is frequent data access. Think of a trending post or a product description that thousands of people are viewing at once. It's much more efficient to serve that static description from the cache rather than querying it repeatedly. Finally, we have leaderboard tallies. Redis is incredibly efficient at handling real-time updates for things like scores or rankings, which would be very expensive to calculate on the fly in a standard SQL database. Now that we understand local caching, let's see how we can distribute content globally. Building on what we just covered regarding local caching with Redis, let's think bigger. When our users are spread across the globe, we need to solve the problem of physical distance. That's where content delivery networks, or CDNs, become essential. The core issue is latency. Even with the fastest fiber optics, it takes time for a data packet to travel from a server in London to a user in Sydney. By using edge servers, we can store static content, things like your images, JavaScript files, and CSS, right in the user's neighborhood. Look at this workflow. It starts with the user request. Instead of that request traveling thousands of miles to your primary data center, it stops at the nearest CDN node. The CDN performs an edge cache check. If the content is already there, it's a cache hit, and the user gets their data almost instantly. This is the performance boost we're looking for in high-scale systems. If the content isn't at the edge yet, we perform an origin retrieval. The CDN fetches it from your main server once, then caches it locally. Every subsequent user in that region will then benefit from that first request. This effectively shields your origin server from being overwhelmed by global traffic. In short, CDNs turn a global distance problem into a local speed solution. Now, we've covered a lot of ground today, from basic client-server models to complex caching strategies. Now, let's bring everything together to see how these components form a complete, production-ready system. Take a look at this diagram. It's the culmination of all the building blocks we've discussed. It might look complex at first, but remember, we've already mastered each piece of the puzzle. Think about the request flow we just mapped out. The user hits the CDN first for static assets, moves through the load balancer to find an available server, and then the server checks our Redis cache before finally hitting the database. This flow ensures efficiency at every step. Always keep our core pillars in mind. We use load balancing for scale, CDNs and caching for speed, and redundancy across the board for reliability. If you can balance these 3, you can design almost anything. As for what's next, we'll eventually look into how these servers can be broken down into microservices and how message queues can help different parts of the system communicate asynchronously.